All right, so for doing this problem, notice what we're being asked to do. We're asked to find d over dx. Now, I've written it this way with the d over dx notation for a purpose, because we're going to be getting into some more derivatives. And so far, basically, all the derivatives we've done have always been d over dx. We've always been taking the derivative with respect to x. And that's going to be changing today. But I want us to bring it back and remember, how do we do it with respect to x so we can then apply it to other things. So, to find this derivative, notice we have x and y over here on the same side. We're going to need to take this derivative implicitly. And so, derivative of x squared, well, that's just going to be 2x. Nice and straightforward, right? But the derivative of y squared is not just 2y. Because remember, y is some function. We're taking the derivative with respect to x. And that's a y, not an x. So that's why we do 2y times y prime. Or, if I'm going to keep my notation consistent here, rather than writing it in prime notation, I would write that as dy over dx. Because remember, dy over dx means the derivative of y with respect to x. And for today's purposes, yes, I want you writing it this way because you're going to see it's going to become really important here in a moment. So, I then am going to go equal to derivative of 25. And it doesn't matter what you're taking the derivative with respect to, the derivative of a constant is always 0. And so, we were just asked here to find d over dx. That's just very generic. Find the derivative of the function with respect to x. I don't have to solve it for anything else. If this one had instead said find dy over dx, I then would solve for this. So I'd like to subtract the 2x and divide by 2y, etc. But I don't even have to do that here, because it just said find d over dx. So I'm done. That's my whole answer there. There's my derivative with respect to x. The new work that we're doing today is finding the derivative with respect to something that's not x. In this case, and in most of the cases we're going to be looking at today, it's going to be d over dt. Now, why over t? Because most things that we're looking at how they change, we're looking to see how they change over time. The derivative with respect to time will tell us how something is changing over time. And so that's why we want to do d over dt here. Now, when we do that, it's the same basic idea as what we just did, where I'm going to do the derivative of x squared, which is 2x, but it's not just 2x. Because that's what it was when it was d over dx. Now, it's 2x times the derivative of x. So it's going to be 2x times dx over dt. So it's chain rule again. The only stuff where I wouldn't have to include this part is if I had a t in the equation. But notice, we're taking the derivative with respect to something that isn't even in our equation at the moment. And yes, we can do that. It just means taking it implicitly. Then when we go to find our derivative of y, much the same. It's going to give us 2y. But again, I don't want to write y prime, because y prime just means a derivative, but we don't necessarily remember y, or with respect to what. So we write it as dy over dt equals 0. And this is now d over dt. We've basically taken the derivative of this entire equation with respect to t. And we're done. And we can use this to figure out all sorts of rates of changes and stuff like that, as we'll see by the end of it. For the moment, though, we can now actually get even more specific with these. So notice the same equation again, but in this case I'm asking you for dx over dt. Not just generic d over dt, but we want to figure out what dx over dt will equal. And as you could probably guess based on the numbers given here, our answer is actually going to be a numerical value. Now remember from the last problem that we just did, we already know what the derivative is with respect to t. That's going to be our first step. We figure out what the derivative is of the entire function with respect to t. But in this case, I know a bunch of values. So I'm going to start plugging those values in. So I know x equals 4. So it's going to be 2 times 4. Next up is dx over dt. Do I know what dx over dt equals? No. In fact, that's what I'm being asked to find out. So I'm just going to leave it as dx over dt for the moment. Plus, 2 times y. Do we know what y is?
Yes.
Yes, so we plug it in. 3. Do we know what dy over dt is? Yes, we're given that up here as well. That's 0.5, so I plug that in. So basically we find that derivative with respect to t, and then we go ahead and plug in the values that were given, and then it's a matter of doing the math from here. So we go ahead and combine our like terms to make things a little bit cleaner. So we have 8 dx over dt plus 3 equals 0. I still need to solve it for dx over dt though. So I subtract the 3 from both sides, and then I divide both sides by 8. And so you end up finding that dx over dt equals a negative 3/8. Just doing the algebra from that second to last line to the last line there. Alright, so now we can look at applying this to other equations that aren't just old x and y. So here you have a fairly familiar looking equation, at least I sure hope so. A equals pi r squared. We can find the derivative of this with respect to time as well. Now, when you do that, what are the actual variables in this equation? I hear r. Yep, r is a variable. What else is a variable? A. What's pi? Yep, it's a number. It's a constant. So remember that as you find the derivative, please find this derivative on your own first, and then we'll come back together here in a moment and check that you're going on the right direction. So to find this derivative, we're first going to do the derivative of a with respect to t. So that just ends up being written as dA over dt equals. Now the pi, remember, stays a pi, because a constant that's multiplied out front of a derivative just stays multiplied out front of it. So it's going to be pi times the derivative of r squared, which is going to be 2r times the derivative of r with respect to time. Now, we could clean this up a little bit, but basically we're done. The last thing I would do is I would just tidy this on the right side a little bit. I'd call it actually 2 pi r dr over dt. And you can put parentheses around the dr over dt if it makes it easier for you to read. They're optional. It just needs to be clear what you mean when you put it in there. Alright, so for finding this one, we're going to be finding the derivative of xy with respect to t. Now, notice that's x times y. We got to use product rule here. So, I'm going to do original times derivative first. So that means the x is going to stay the same. And it's going to be times the derivative of y. Now again, I don't want to write y prime here because y prime is ambiguous. When we see y prime, it usually means dy over dx. But this is actually supposed to be dy over dt. So spell it out. Be specific here. We want to make sure. Then we are using product rule. So plus, now the derivative of x with respect to t. So dx over dt times original, so times y, equals 0. Make sure that you made that a 0 on the right hand side, because of course derivative of any constant is going to be 0. Alright, now we start plugging in our values because we're actually asked to find dx over dt, and we have some values. So I can start plugging those in. I ended up finding that's 3 times dy over dt. I have that. That is known to be 6. Plus dx over dt. Well, that's what I'm trying to find, remember, up here. So I'm going to leave that as dx over dt. And then times y. I don't know what y is. But if I'm going to figure out what dx over dt is, I need to know what y is.
Solve for y.
We can figure it out, can't we?
Easy money.
So if you got stuck at that point, since we know what x is, plug 3 in for x up here. What would y equal?
Oh, y would equal 8.
If 3y equals 24, then yes, y equals 8. So then you can actually go and you can plug that in for y now that we've found it. So sometimes you actually have to go and find that value. From here, solve it for dx over dt. And so when we solve it algebraically, we subtract the 18 from both sides, then we divide both sides by 8. We get negative 18/8. Go ahead and reduce that down. You should get an answer of a negative 9/4 or negative 2.25 as well. Now, this problem that you see here, this is very indicative of the direction we're going. We've actually been in a process of leading up to being able to do problems like this for a little while. When we started doing implicit differentiation, we were setting things up so you had the skills to find derivatives with respect to t. And we need to be able to take derivatives with respect to t so we can answer questions like this. These are called related rates problems. They have all sorts of fancy things. But basically, we're talking about story problems where we can figure out how quickly some quantity within it is changing. Now, as you take a look at this problem, the first thing we want to do is we want to write an equation that represents the situation. Now, this situation that we're being told about here, notice it tells us about the area of a circle. Because when it tells us the radius, of course, radius is part of what we need to know in order to be able to figure out area. So those are the clues that tell me that I want to start with this equation, a equals pi r squared. Gee, kind of like that one we looked at earlier, right?
Oh yeah, of course.
So we already have an idea about what this was going to look like. So I know that I'm going to be using this equation because, of course, the situation describes area. It's asking how quickly the area of the circle is growing. So if I want to know how quickly it's growing, I need to figure out the rate of change with regards to time. In other words, find the derivative with respect to t. So derivative of a would become dA over dt equals, and the same thing on the right. Now we already did this problem earlier, right? So we know it's going to be 2 pi r times dr over dt. Because remember that dr over dt, that we got to include because it really is chain rule, because we're finding the derivative with respect to t, not the derivative with respect to r here. But it means it's all rates of change. Now, let's see what all we know now. Do I know what dA over dt is? Well, that's the rate of change of the area. Well, that's what we're being asked for. We're being asked how quickly is the area of the circle growing. So, no, we don't know it, so we're going to leave it as dA over dt at the moment. Equals 2 pi, now times r. Do we know what r is?
Yes.
Yeah, we know r is 20. So it's going to be times 20, and then times dr over dt. So do we know what dr over dt is?
Yes.
Yes, because that's the rate of change. That's how quickly the radius is changing with respect to time. So radius is changing over time by 3 inches per minute. So I put the 3 in there. Actually, I should probably keep that the same color. There we go. And so the area then is changing by whatever that value is. I can go ahead and calculate that. I'll go ahead and leave it in terms of pi. So 2 times 20 is 40. 40 times 3 is 120. So I'll call that 120 pi.
That's some quick math.
Now, this problem, though, it's missing something from its answer because this is actually talking about a rate of change, about something real. Well, I need units. The nice part, though, is finding the units is pretty easy because I can just look over at this. It's A over T. What is A measured in?
Inches. Squared.
Ah, yeah, it's area, right? Area is square inches. So that's going to be square inches per, what's T measured in? Minutes. So it's square inches per minute. So what this is saying is that at this moment, if you have a circle with radius of 20 and it's increasing by 3 inches per minute, that means the area of that circle is increasing by 120 pi square inches per minute. And so we're done. We now know how quickly the area of the circle is growing. All right, now in this particular problem, we got a circle with radius 12. Its area is known to be shrinking by 5 square inches per hour. How quickly is the radius changing? So obviously, we're dealing with another problem where we have A equals pi r squared as our starting thing. And again, I'm trying to figure out how it's changing over time. So I want to find the derivative with respect to time again. We already know what that is. dA over dt equals 2 pi r dr over dt. And then I need to start plugging in everything that I know. All right, so once again, do I know what dA over dt is? Well, if you were just assuming that this problem was just like the last one, you'd be thinking no, but we actually do. Because we do know how the area is changing over time. Because you'll notice the area is shrinking by 5 square inches per hour. So that means that dA over dt, but even that, I got to tweak just a little bit, right? Because if it's going to be shrinking, it's a -5. So we're decreasing by 5, so I'd say d over dt is a -5. All right, equals 2 pi times radius. Do I know what the current radius is?
Yep.
Yes, that's 12. Next up, dr over dt. Do I know what that is? No, in fact, that's what we're being asked, because we're being asked how is the radius changing over time. So it's going to stay a dr over dt.
Oh, God.
And then we're going to solve that equation.
-5 over
All right, so
pi.
I end up dividing both sides
dr over dt.
by 24 pi to get dr over dt.
Dr. T.
And so, if it equals -5 over 24 pi, and so we end up getting then that dr over dt is about, because of course, we're going to have to do some rounding if I actually calculate with the pi in there. Yes, you can choose to leave it like this as well, because I didn't specify. But I'm going to go ahead and round it off. I get about, oops, forgot the negative sign, 0.0, let's call it 66. Now, what are our units here? Well, remember it's dr over dt. What is the radius going to be measured in here?
Inches squared over hour.
Well, radius
It's inches. It's just inches.
was measured in inches. So it's only inches. This one's not square inches because I'm measuring the radius, not the area. So it's inches per hour because it's over time. Time is measured in hours here. So it's going down by 0.066 inches per hour. Not changing too quickly.